Can you see my screen?
Yes, we can. So please, Pratik, go ahead. And
Okay, so good afternoon, everyone. Thank you for having me here. I am Pratik Mishra, a second year PhD student at the Biomedical Engineering Department of University of Toronto. The topic of my research is automatic detection of behaviors of risk in people with dementia using unsupervised deep learning. Dementia is a syndrome that involves progressive impairment of cognitive functions such as memory and thinking. It can lead to a lack of impulse control. The behaviors of risk in people with dementia can be described as clinically important behaviors that can put them and the people around them at risk of injury. They encompass a range of activities such as hitting, kicking, pushing, throwing things, among others. With the progress of dementia, it becomes necessary to provide supervision and support to the people with dementia in their activities of daily living, which is mostly fulfilled by long-term care homes. However, long-term care homes can suffer from understaffing and lack of financial resources, which makes it difficult for the staff to continually monitor the residents. Therefore, automatic identification of incidents of behaviors of risk in people with dementia would be an important tool to raise alarms to take appropriate interventions. Here are some of the examples of normal and behavior of risk events captured as part of the collected data. In the normal events, you can see people walking in the hallway or empty hallways. As part of the behavior of risk events, you can see a participant kicking a co-patient on the wheelchair on the top left and a patient banging on the nursing station door, among others. A pilot study was conducted using data from one participant. The training set composed of 24 hours of video data representing only normal behavior, and the test set composed of 11 hours of video data, out of which 80 minutes represented behaviors of risk class. A 3D convolution autoencoder was trained on normal behavior data and identified behaviors of risk as anomalies during deviation using deviation in reconstruction error. Two loss functions were investigated, particularly the mean square error loss and gradient loss. The performance of 3D model was compared for three different cases: the mean square error loss, the gradient loss, and a composite loss function of mean square error and gradient loss. The best performance was for mean square error loss function with a score of 0.75 for AUC for the ROC curve and 0.259 AUC for the PR curve. My research will answer the question, how can deep learning be used to detect behaviors of risk in people with dementia using video surveillance data while safeguarding their privacy? The following are the objectives as part of my research. As part of the pilot study, it was observed that there were a significant number of false positives in the results. Hence, there is a need to address the false positives and make the performance more reasonable. Hence, as part of the first objective, I plan to develop deep learning methods to detect behaviors of risk using videos with reduced false positives. Further, the camera recordings contain identifiable information, which is a privacy concern, extracting only the structural and movement information of the participants, while hiding their appearance can bring a sense of security to the participants. Hence, I plan to develop privacy protective deep learning methods using anonymized video data to detect behaviors of risk as part of second objective. Further, it was observed during the pilot study that some of the behavior of risk events were missed during the data labeling process, leading to noisy labeled data. The process of data labeling is expensive, time consuming, and prone to human errors. Hence, as part of the third objective, I will be developing deep learning methods to detect behaviors of risk using partially labeled data. The 3D saying method, as part of the pilot study, detected anomalies in the scene. Hence, the method was sensitive to changes in the scene, such as number of foreground objects. This led to a significant number of false positives. In order to reduce the number of false positives as part of the first objective, the plan is to extract image patches from videos containing participants in the scene and train an anomaly detection model on these patches rather than the entire scene. The patches will be extracted using object detection algorithms. The trained anomaly detection method will be used to generate anomaly scores for each participant in the scene. Thereafter, the anomaly scores for all the participants within a frame will be aggregated to generate frame-based anomaly scores and classify the input video clips as behavior of risk or anomaly. The reasoning behind this is that the image patches will make the method focus on behaviors of individual participants rather than the entire scene. Coming to the second objective, During the data collection, the cameras didn't capture the behaviors of risk events in the private room of the residents due to privacy concerns. As part of the second objective, I will extract body zones information from raw videos. However, cameras like Sanitaire 2 from Altum View exist that capture body zones information directly from the scene, thus protecting the privacy of the participants during the data collection phase. The plan is to extract body zones information using a human pose estimation algorithm for the people in the scene and detect anomalies in the poses of the individual participants rather than the entire scene. This will be done by training a sequence-based classifier on the body zones information of the participants in the scene and generating anomaly scores for individual participants in the scene. The anomaly scores for all the participants within a scene will then be aggregated to generate window-based anomaly scores, which will be used to identify normal or behaviors of risk windows. Coming to the third objective, the training set will consist of positive and unlabeled data. Positive data is used to refer to behavior of risk samples, and negative is used to refer to normal behavior samples. As part of the process, one-dimensional video embeddings will be extracted from the input video clips using a self-supervised contrastive learning approach. Thereafter, reliable negatives will be identified in the unlabeled data using positive video embeddings using clustering-based approaches. Once the reliable negatives are identified, an anomaly detection classifier will be trained on the reliable negatives. The trained model would be capable of identifying behaviors of risk and normal clips. I conclude my presentation with the following observations. From the results of pilot study, it can be concluded that it is indeed feasible to detect behaviors of risk events as anomalies from surveillance videos. However, there is a need to reduce the false positives and address privacy concerns associated with the video data. I'll be addressing these shortcomings as part of my PhD research. Thank you for your attention. Kindly let me know if you have any questions.
Hi, Pratik. Thank you. Thank you very much. I think I missed one thing. Are you collecting your video data or do you have already a data set to work with?
Yeah, the video data was already collected, so I already have the video data.
So you have collected yourself the data?
No, the data was collected before I joined my PhD.
Oh,
So
okay.
yeah, that was fortunate.
Yeah, it is. Thank you. Thank you.
All right.